In this video, we're quickly calculating a one proportion confidence interval using the built-in TI-84 function one prop z interval. Then we're going to follow up by expressing the confidence interval in terms of a margin of error. So we're doing this in the context of an example where we're told that we have a survey of 400 registered voters. So n is equal to 400 here, and we're told 232 of them support a proposed ballot measure. So we normally call that x. We're going to say x is 232. And we're asked to get a 95% confidence interval for the true proportion of voters in favor of this legislation. Now, just a quick reminder of the context here. One proportion confidence intervals need to be built on an underlying binomial process. And we meet that standard here because each voter is either counted as a success, meaning they support the legislation, or they're a failure, meaning they don't support the legislation. And one last thing before we start pressing buttons, the calculator is going to do this anyway, but I'd like to write down the sample proportion in favor of the legislation. So we normally call that p hat, or in some books it's p prime, and that's 232 divided by 400, giving us a sample proportion of 0.58, and we could also call that 58%, and that's called the point estimate for the population proportion. So let's head to the TI-84 to see how we can quickly generate the 95% confidence interval for the proportion of voters in favor of this ballot measure. So we press Stat, then we go over to Tests, and we're going to arrow down to one proportion z interval. And you can see the calculator's using the same notation where x is the number of successes. So we had 232 successes. Our sample size was 400. And we're using a confidence level of 0.95, which is actually the default value for the TI calculator. And we go ahead and hit enter. And there's our one proportion confidence interval. It's stated as an interval from 0.53163 to 0.62837. And we're going to round those off a little bit. So we just round those to the thousandths place, and we get 0.532 for the low end and 0.628 for the high end of the 95% confidence interval. So it's probably more intuitive to express these proportions as percentages. So we can say this confidence interval is 53.2% on the low side and 62.8% on the high side. Now, as a follow-up, we might want to express this confidence interval in terms of a margin of error, and that's sometimes also called an error bound for proportion, or EBP. So the margin of error is just the size of the plus or minus that we put on the point estimate, and we can get that by computing half the width of the confidence interval. So we're just going to take the upper end of the confidence interval, that's 0.628, and then we subtract the lower end of the confidence interval, and that was 0.532. That gives us the width of the confidence interval, 0.096, and then we can divide that answer by 2, and that's going to give us the margin of error. So there's our margin of error written as a decimal, that's 0.048. And again, this is probably more intuitive if we write it as a percentage. So our margin of error is 4.8%. And so we can write our confidence interval as the point estimate plus or minus the margin of error. As a decimal, that looks like 0.58 plus or minus 0.048. And as a percentage, that's 58% plus or minus 4.8%. In the next video, we learn how to use the z-interval function in the TI-84 to compute a one mean confidence interval when the population standard deviation is known. I'll post a link to that video at the upper left, and I'll see you there.